Hello everybody. Is anybody here? Okay, Zero is watching. All right. I'll wait for somebody join this. Oh, hi, Vihu. Yeah. Hello. So you can ask any questions in the chat, and then I'll try and answer it down here. Okay. Okay. From my side, it's all Zero watching. I don't know if anybody is watching now. Good. Suddenly 10 watchings. Okay, that's good. All right. So any questions, or let me introduce the today's session first, and then you start asking question. Okay. Well, let's just wait for 5 minutes and see if there are more students coming in the in our chat room or live streaming. Okay. Wow, 14. And now you can start organizing your questions. For those of you who has just came in, you are not in the wrong place. Now it's the QBUS5002 final exam review plus consultation online live streaming held by Tony. So if you got any question, just ask me in the chat. In the chat, you must first log on YouTube using your Gmail account in order to chat in our chat room. Okay, ready. Okay, so many students are ready. Okay, good. So if you're ready, then you just ask questions, okay? If you don't have any question, then I'll probably find some common issues or key areas of understanding or difficulty areas and explain them to everyone. So which one do you prefer? You ask question, or I just find some frequently asked questions and explain to everyone? Nobody is talking. Explain first. All right. Where shall I start? Okay. So it's already 4 minutes since our live streaming started. So let's just go through some key issues that students may face in their revision. So in the final exam, as we know, there is a final exam information PowerPoint slides uploaded by Burn, and within which there's very detailed instructions on what will be examined and what will not. So I think for the second part of this semester, the most most important, but the most probably the hardest thing that everyone need to know, first of all, is hypothesis testing. This is definitely a part that everybody need to understand and then apply. And the second part is linear regression. So those two topics are the basic things that we learn in the second part of this whole semester. And we also got some financial ratios, time value of money, or time series. All of three topics are not that hard, so I don't wanna pay more attention on them today. So what we're gonna be focusing on are the hypothesis testing and linear regression. Okay. So first of all, let's have a look at hypothesis testing. From your mid-semester exam, your performance from mid-semester exam, one thing that not all students are really understanding is central limit theorem. So today's consultation or today's review, we just start from central limit theorem, okay? So do you have any idea what is central limit theorem? Or what does a central limit theorem tells us? So basically, for central limit theorem, we are focusing on estimating two things. One is population mean, and the other is population proportion. And basically, central limit theorem is just telling us in order to estimate population mean or population proportion, what kind of statistic shall we use, and what are their sampling distributions? So firstly, for the estimation of population mean, we got a central limit theorem for X bar, which is the sample mean. So based on central limit theorem, the brief idea of central limit theorem is that whenever n is greater than 30, which means a large sample, and no matter how the population is distributed, the sampling distribution of sample mean always follows what kind of distribution? Normal, exactly, normal distribution. And what is the mean of this distribution? Mu, good. And what is the variance of this X bar distribution? Sigma square divided by n. Very good. Okay. So, in order for us, not in order for us, but why do we bother thinking about central limit theorem, and how, what's the point of knowing the sampling distribution of the sample mean X bar? You probably have that question, right? Okay, I can tell you here that the two main applications of central limit theorem are confidence intervals as well as hypothesis testing. Why is that? Now, let's firstly focus on the confidence interval part, okay? So for example, if you want to build a confidence interval of your estimated population mean, then what would you do? So if we know the sampling distribution of the sample mean, then we probably know that if this is the true value of the population mean, and the sampling distribution of sample mean must follow some normal distribution like this, right? This means if we take any sample, it's very likely to have some sample or observed sample means around the true value of the population mean, but at the same time, we still have chance to be very lucky. For example, the Mexico wins the Germany yesterday in the World Cup, right? So there are still very small possibility that we can be so lucky to have a sample mean that is very far away from the population mean. Everyone agree on that? Okay, so what we want to do is that every time we take a sample here, for example, we really want to build a interval. For example, a confidence interval like this. Let me change another color probably. Okay, I'll use red one. Okay, build an interval like this. So every time we have a sample mean, we build an interval. Every time we have sample mean, we build an interval. And what we want to achieve is that we want, for example, 95% of all those intervals includes the true value of the population mean mu. Okay? So I'll repeat it again. So firstly, every time we take a sample, we will get a different observed value of the sample mean. And we know its sampling distribution is like this, right? And what we want to do is that we really want to create an interval, which means using x bar plus something and minus something and create an interval. And for each interval, for all the intervals that we created, we want 95% of all those intervals includes mu, the true value of the population mean. And this 95% is what we call the confidence level, or 1 minus alpha, which is 1 minus alpha. Everyone happy with that? Okay. So if this is the confidence level, so let's see what should be the boundaries, or how wide should the confidence level to be in order to make 95% of all those intervals include the true value of the population mean mu. Then you probably know the answer, right? So if x falls between some intervals like this, and then we know if on both sides the probability in total is 0.05, which means on one side is 0.025, then we probably know that if we observe x inside this area, then the interval must include the true value of the population mean. And if we create an interval outside of this area, then this interval will not include the true value of the population mean. Okay, so that's the whole point of a confidence interval. So then, how does this confidence interval be built? So basically, if we look at any confidence interval here, for example, let's take a look at this one. And we know that if we want to calculate this confidence interval from LCL probably to UCL, and we can do it in Excel very easily. However, in the old times, we don't have Excel. So what we need to do is standardization, okay? So by standardization, we want to make the LCL, we want to find the standardized version of LCL, and as well as a standardized version of UCL, probably here. So as we all know, the probability on the two sides of LCL and UCL should be the same as the significant level, or 1 minus alpha. So each side 0.025, that side 0.025. Therefore, we know this side, it should be z 0.025, and this part is minus z 0.025. All right. So what can we know from here? Therefore, let's see. LCL, if we standardize it, we will get minus z. And if we UCL and standardize it, we will get the positive z. So how do we standardize a non-standard normal variable? We minus its mean and divide it by its standard deviation, right? Okay, so if we use LCL minus mean, for example, mu, but here we suppose x bar is our observed mean, okay? So LCL minus X bar divided by sigma divided by square root of n, which is the standard deviation of X bar. And this one must equal to minus Z 0.025. So if you solve LCL here, you will find LCL is just equal to X bar minus Z 0.025 times sigma divided by square root of n. So this is the formula that you can find in your formula sheet, right? Can you see that? Okay, so the confidence interval, therefore, is nothing but just the standardized, or by standardization, we can get some values plus on x and then minus x. So if you calculate UCL, then it must be x bar plus, because here it will be plus for UCL, right? And plus Z 0.025 sigma divided by square root of n. So this is how we calculate confidence interval. So what's the point of telling you everything about that? So basically, what I want to tell you is that we can see if from central limit theorem, it's because you know the sampling distribution of the sample mean that you can really standardize them, right? You can standardize them. So by standardization, we can really get the formula of LCL and UCL. This means if you really want to use like sigma divided by square root of n and this normal distribution, it must follow, at least meet the requirement of the central limit theorem. Okay, so that's why every time, sometimes in your question, after you calculate a confidence interval, you are required to state any assumptions that you needed in this question. Okay, so this is when you need to talk about central limit theorem or a normal population. Okay, so now let's go back and see this LCL and UCL and try to find all the sampling distributions and all the confidence intervals by ourselves, okay? So if we observe LCL and UCL here, we can find an interesting fact, which is the confidence interval always has a center of the point estimate of the population parameter, right? So this is the point estimate, which is X bar. So the center of any parameter confidence interval is X bar, for, not X bar, but the population, the point estimate, right? And by plus or minus 0.025 times sigma divided by square root of n, and we can see Z 0.025 is just a critical value, right? A critical value of any distribution. It can be Z distribution, which is standard normal, or in future, not in future, but you've learned it can be T distribution, right? Okay. So T distribution. And for this part, it is actually nothing but the standard deviation of X bar, isn't it? So this is the standard deviation of X bar. Therefore, in general, if we make it more general, okay? So X bar, as we mentioned, it's actually the observed value of the a point estimator, right, which is the sample mean. Therefore, for any population parameter, it's actually, the center must be a point estimator, right? Estimator. And then plus or minus Z something or T something, which is a critical value, right? And then times something. So this thing is actually the standard deviation or the standard error of this point estimator itself, okay? So times the standard error, which is SE, or standard deviation of the point estimator itself. Okay, so this is what we call a general form of confidence interval. So this means if you want to estimate anything, then you only need to know what is the point estimator, what are the critical values, and what is the standard errors of the point estimator. And then you can derive the whole formula, okay? So Jennifer Feng has a question. Will there be problem about calculating p-value of t-distribution? The answer must be no, because you cannot find a p-value of a t-distribution in any statistical tables, okay? So you don't need to worry about that. All right, now let's continue thinking about this general form. So once you know the general form of this confidence interval, then all you need to do is simply knowing all the point estimators, and then you'll be fine. For example, if we want to estimate mu, what is the point estimator of mu? X bar, right? From central limit theorem, we know it follows a normal distribution or t-distribution based on whether the sigma is known or unknown. But the mean is always mu, and variance is always sigma squared divided by n, right? So, namely, if sigma is known, let's try the general form. Well, I'll write down the general form again, which is the point estimator plus or minus z, not z, but critical value times the standard error of the point estimator, okay? I'll just use theta hat over there. So this point estimator, we call it theta hat, for example. So if sigma is known, as we've derived just now, the point estimator must be x bar, right? And plus or minus, critical value must be z half of alpha, right? Z half an alpha. And standard error of x bar is square root of sigma squared divided by n, so it's sigma over square root of n. Everyone happy with that? Okay, so this is quite awesome, very easy, right? Now, if it is unknown, you probably know that if it is unknown, it must follow what distribution? A t-distribution, which has an n-1 degrees of freedom, right? Okay, so if it's unknown, sigma is unknown, we can only use sample standard deviation, which is s divided by square root of n, and use t half an alpha n-1 as a degree of freedom, or t n-1 half an alpha, whatever you like, okay? So all of those are the simple population mean, okay? Now, if we look at the population proportion P, what is the point estimator of the population proportion P? What is the point estimator? P hat, right? And how is it distributed according to central limit theorem? It's again normally distributed. So Super Yan has a question, will this live video be recorded? Yes, it will be recorded. So don't worry if you have other things to do, okay? I know tomorrow morning is going to be your QBUS5080 exam. So good luck for all of you for the exam, okay? So P hat follows a normal distribution, and the mean must be the true value of the population proportion, and the variance is actually P times 1 minus P divided by N. So if you have no idea about this, you'd better, okay, I can't say anything bad here, but you need to know it, okay? This is central limit theorem. It's very likely to be in your multiple choice question, okay? So Cecilia Tong is asking, when we calculate the confidence interval, do we need to interpret? It depends. Like, if I were you, I will always interpret the confidence interval after I calculate 1, okay? But I think there should be some questions like interpret the confidence interval that you've calculated, okay? So don't need to worry that much. All right, so let's do it again. Let's continue. So p hat also follows a normal distribution. Therefore, let's follow the general form. Point estimator plus minus critical value times standard error. Therefore, the confidence interval is given by the p hat plus or minus what? Critical value should be z half of alpha because it's normal distribution. And standard error is just the square root of the variance, so which it must be p times 1 minus p divided by n. However, we have no idea of the value of p, therefore we use p hat, okay, in the calculation of p. So all of those are the single populations, and for two populations, everything is just similar, but just sort of complicated, so don't worry. I'll just take one example, and for all the rest of the things, you just do it in your own time, okay? So for example, if we have two population mean, we want to know the difference between two population means, which is mu1 minus mu2. So if it is mu1 minus mu2, we know the point estimator must be x1 bar minus x2 bar, right? Okay, now, what is the sampling distribution of x1 bar minus x2 bar? Given that x1 bar follows a normal distribution of mu1 sigma 1 squared over n1 over n1, and x2 bar follows a normal distribution with mean mu2 and sigma 2 squared over n2, then what is the distribution of the difference of x1 bar and x2 bar? I think you've learned this before your Miss and Maths exam, and hopefully you still remember. So the difference distribution is still a normal distribution, and the mean becomes what? Yeah, the difference between their own means, okay? So that makes x1 bar, x2 bar an unbiased estimator of mu1 minus mu2, okay? And for the variance, since here we have an assumption of independent populations, right? So if those populations are independent, then the variance, add them together, should be just the sum of their variance. So it's sigma 1 squared over n1 plus sigma 2 squared over n2, okay? Therefore, it's very easy to find out the confidence interval, which is x1 bar minus x2 bar, and then plus or minus what? Critical value again. Critical value is still z half an alpha and times the standard deviation or standard error, which is sigma 1 squared over n1 plus sigma 2 squared over n2. Is that right? So as we can see, many of the students are complaining there are too many formulas to apply in confidence interval, but we can see if you know the sampling distribution of all of them, it's not really hard, right? So you can basically derive everything that you've learned, okay? All right, so mu1 minus mu2. Then this is definitely when all the sigmas are known, right? So if sigma 1 squared and sigma 2 squared are known but equal, but unknown but not equal, there are two other formulas, but just a little bit alternation on their standard error. So all of those formulas are in your formula sheet, so I don't want to spend too much time on this. So all my point here is that you really need to know all those any of the confidence interval can be calculated in this way, okay? Anything can be calculated in this way. All right, so that's all about confidence interval. We know we still have P1 minus P2, so similar. You just look at the formula and know it's a normal distribution with a mean P1, the point estimator is P1 hat minus P2 hat, and the mean is P1 minus P2. Variance should be P1 times 1 and then minus P1 divided by N1 plus P2 times 1 minus P2. Oh my god. Oh my god. P2 divided by N2, something like that, right? So this is a sampling distribution. So your task when you go home, it's simply complete all this sheet, okay, and try to understand everything in this sheet, okay. All right, that's all about the first application of central limit theorem. As we can see, once we know the sampling distribution, and we can actually calculate a confidence interval. That's why central limit theorem is very, very important, okay? We can say central limit theorem is the stone, the capstone, not the capstone, what stone? The base stone, basement, yeah, the base of all inferential statistics, okay? So since we know how X bar is distributed, we really know how to construct confidence interval or perform hypothesis testing. Okay, so we've just discussed the confidence interval, but we haven't touched the hypothesis testing. Now, let's spend some time doing hypothesis testing. So, some of you probably say, okay, we do have a general form of a confidence interval. So do we have a general form of our test statistic? That is, the answer is yes, okay? So when we're doing hypothesis testing, the key thing or the key calculation part is about the test statistic. It can be Z, it can be T. I think in QBUS5002, you use Z star or T star as the notations of a test statistic. Okay, so I'll just use one example and then all the rest things just goes to your own working, okay? So the general form of a test statistic, either Z or T, is calculated just by the standardized version of the point estimator, okay? Standardized version. Because in the null hypothesis, we always have some population parameter equal to some value, right? Okay, so when we calculate the test statistic, we always assume the null hypothesis is correct, right? So in this way, we construct our test statistic by using a X bar minus the hypothesized mean, which is mu0, it depends on what you assume, okay? And divided by sigma divided by square root of n, which is the standard error. So in general, the general form can be regarded as a theta hat, which is any estimator, okay? Any estimator, minus the hypothesized value, like theta 0, and then divided by the standard error of theta hat, okay? Standard error of theta hat. So why is this useful? Because sometimes in your linear regression analysis, you probably need to perform a hypothesis testing on betas, which is the individual significance t-test, right? So for example, we know beta I equal, for example, 0, and we want to test if beta I is not equal to 0 or whatever, right? So in this case, generally speaking, the t-statistics or the p-values will be directly given in the Excel output. However, if they are not given, then you probably need to think about what is the test statistic. Especially the key problem I've found in your major assignment is that everyone knows how to perform a individual significant test and how to interpret the individual significant test. But only a few of you has expressed their understanding of constructing the test statistic, okay? So the test statistic should be a t-statistic, which follows a t-distribution. And it is actually also calculated by the point estimator standardize it, okay? So we know the point estimator here is just, it's beta I equals 0 or beta I not equal to 0. Sorry, this is another common mistake that students are making, okay? On the hypothesis, we are making hypothesis on the parameters instead of sample statistics, okay? So we need to use beta I here instead of beta I hat, okay? So beta I hat is wrong. Similar to the mean, if someone say, okay, now hypothesis x bar equals 0, x bar not equal to 0. This is absolutely wrong, okay? Because we are making hypothesis on the population parameters, okay? All right, so that's one key thing that some of you might probably make a mistake on. So let's continue constructing our test statistic. So for this test statistic, it's just calculated by beta I hat and minus beta I, our hypothesized beta I, divided by the standard error of beta I hat. So where can we find this standard error? So for this standard error, it's actually in your Excel output. You can see a lot of things here. And the first column is coefficient, and the second column is just the standard error, right? Therefore, the t-statistic is just calculated by your observed coefficient, which is beta I hat, minus beta I. Beta I is 0 here because we hypothesize it to be 0. And then divided by standard error, which is from the second column of your Excel output. Here is the standard error, okay? And this bad boy follows the t-distribution with degree freedom n minus k minus 1, okay? So many of you have missed this step in your major assignment. That's why you got some marks deducted from your answer, okay? And again, for the decision rule, everyone knows it, right? It is, for example, it is p-value less than alpha, we reject, or the t observed value of t greater than the critical value, and then we reject the null hypothesis, something like that. So everyone knows it. I don't want to spend too much time on that, okay? So if you got any problem, just ask me. Okay, so what I want to mention here is actually I know most of you is able to follow the steps, the 7 steps for the hypothesis testing and get some marks in your final exam. But you know, final exams somehow will test on your understanding of the knowledge. For example, in your mid-semester exam, we've got an understanding of rolling a die, right? So when rolling a die is actually testing on your understanding of central limit theorem, okay? But I believe everyone somehow knows something about central limit theorem, like n greater than 30, then x just follow normal distribution approximately. But when you apply the idea in a rolling a die example, then probably you have some problem in applying the central or just understanding of the central limit theorem, okay? So my point here is that from central limit theorem, what we can know is the sampling distribution of our estimators, because we really want to forecast or estimate population mean or population proportion, but we have no idea about the true value of them. So what we can do are the 2 things. One is confidence interval. We can construct an interval and say that we have 95% or any 1 minus alpha percent confidence to say that the interval will include the true value of the population mean or population proportion. And we can also do a hypothesis testing. And testing, we make a hypothesis on the population parameter first, and then use a sample to test if our hypothesis is right or wrong, okay? So all those things, confidence interval or hypothesis testing, is based on the conclusion of the central limit theorem, okay? So that's how the central limit theorem is important. Now it's the question time. Crystal Hu is asking statistics like standard error, should we need to calculate by ourselves or the exam paper would give us? All right, it really depends. For example, for the standard error, if it is a sample mean, so do you know what is the standard error of sample mean? You must know it, right? It's sigma divided by square root of n. It's just square root of the variance. So if you are given sigma, you're given square root of n, you must know what is the standard error of this. However, if it is in a, for example, linear regression problem, the linear regression problem is that the problem is actually there is a calculation formula of the standard error of any beta hat, and it's in your textbook or in your lecture slides, but I don't think they are. Oh no, I can't say that, but I've never seen the exam paper, but I don't think you are required to calculate the standard errors by yourselves. Just like what Ben said in your exam review, like lecture slides, you are not required to calculate beta I hat. So you will be given probably some outputs, and once you know some outputs, you are required to complete all other outputs, okay? So that's my point here, all right? Okay. Do you have any other questions in terms of the central limit theorem stuff, which includes in confidence interval plus hypothesis testing? So those two parts are very important for a final exam. All right, now, if you're all happy with those parts, the second part we're going to cover is regression. So basically, we really learned a whole lot from the regression analysis, but one problem I've found from the students is that you don't really know the whole picture of the knowledge of the regression analysis, okay? The whole picture. So what I want to illustrate here is that I want to structure all the knowledge you learn from the regression analysis in a way that you can understand what's going on, okay? So if you're ready, let's try and get a sort of 5-step of a regression, okay? So firstly, you can sort of recall what you've done in your major assignments, in your major assignment or group assignments, and this is just a summary of what you've done in your major assignment. Okay, so step 1 is actually I would like to call it the understanding of data. So in this part, you'll probably draw some scatter plots and see if there are linear relations or quadratic relations or exponential relations or log relations, something like that. Again, in understanding of data, you also need to think about which of the data or which of the independent variables are numerical and which are categorical. So we know that for categorical data, you probably need to convert all the categorical data into what we call dummy variables, right? So dummy variables. Categorical, okay, categorical data. So that's all about step 1. So after step 1, you probably have some idea of what is your regression model look like, right? Whether it is x or x squared or e to the power of x or whatever it is, okay? And we also need to know if you need to include like male and females, this dummy variable, right? Like 1 stands for male, 0 stands for female, anything like that. So in the first step, our main task is just determine the relationships between our y variables and x variables, okay? Another technique probably be the correlation matrix. So I will write 1 here. So from graph, we can see something. Secondly, we need to identify the types of data, right? Whether it is numerical or categorical. Thirdly, we need to think about their correlations. Discuss on their correlation. So by observing a correlation matrix, we can actually know the correlation between y and all the x's, and even the correlation between x's, right? The 1, 1, 1, 1, 1, this is something, 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 okay? So for correlations, many of your assignments has discussed the problem of multi-correlation. That is good, but you just forget the easiest thing, which is the correlation between y and all independent variables. So basically, you can sort of see if there is any variable does not really affect y, or does not really correlated, is not really correlated with y if they have very low correlation. So if you observe a very low correlation like 0.01 correlation against y and x, then probably in your individual test of significance, you'll still have insignificant result for this specific x, okay? So correlation can somehow give you an idea of which of the independent variables are important and which are not. And also, we can look at the existence of multicollinearity, okay? So that's about the first step, which is the understanding of data. So all the steps I've mentioned today can be an aspect of your exam question, okay? So just think about it carefully, okay? All right, so this is step 1. Now step 2. Step 2 is just model selection and estimation. So after you sort of have some understanding of the data, you need to select a statistical model or a linear regression model, right? So one thing I want to mention here is that many of the students get confused about a statistical model or linear regression model and their estimated result, okay? So when we talk about a model, especially in your major assignment, okay, I can see a lot of mistakes in details about distinguish between a model and the estimated equation, okay? So when we talk about a model, it's very, very clean one. What do I mean by clean? So a clean thing should not include any hats, okay? No hats, okay? So for model, it should be y equal beta 0 plus beta 1 x1 plus beta 2 if there is any d2 plus beta k xk. And never forget to plus epsilon, error term here, okay? So this is what we call a model. So if in your exam you are asked what is the model that you applied in this linear regression analysis, you shouldn't write any numbers here, okay? Instead, just put all the parameters beta here, y without hat, beta without hat, and don't forget to put an error term, okay? Never forget to put an error term. So what does a model mean, or what does this model depict? So when we talk about a model, it's more like a population concept, okay? It's more like a population concept. This model actually has two parts. The first part is when we take a conditional expectation on each x, we can actually get a formula here, which is just a deterministic line. Beta 1 x1 plus beta 2, for example, d2, blah, 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 beta k xk. So this is the first part, which is the straight line. It stands for a straight line on this plane, right? And the second part well, we know this part is deterministic or stochastic. It should be deterministic, right? So this part is deterministic. Deterministic means not random, okay? Not random. This means every time you have input of x, you will get only one value of y, okay? 1x, 1y, 1x, and 1y, okay? So this means deterministic. And the second part of this model is actually a stochastic part, which is epsilon. We know this epsilon is assumed to have a normal distribution and mean of 0 and variance of, for example, sigma square, sigma epsilon square, okay? And we have a lot of assumptions on epsilon. One is normal distribution, second one is equal variances, and then they also need to be independent, right? And identically distributed. So we made a lot of assumptions on error term, which will be covered more about that on step 5, which is the model assumptions. But so far, you need to understand a statistical model is sort of a population generating rule. It's a rule of a generating population. So based on this rule, whenever we have an x, we first have a deterministic value, which is the expected value of y. At the same time, based on this part, deterministic part, we still need to plus an error term, which is normally distributed. This means for any observed x, we can have y values around the straight line, right? So for any given x, we will have a value around the straight line. So any given x around straight line, any given x have a round straight line, any given x have a round straight line. Okay, so we have a population like this, okay? So the population is what the model describes, okay? However, it's just like when we estimate a population mean or population variance. Do we really know the value of the population stuffs? Not really, right? So what we need to do is that we need to observe some value of y and x, which is just to take a sample from this population, right? So if we take a sample, we can have some sample like this, okay? But it's never equivalent to the population. And based on this sample, we can actually find a best line to describe all the sample data, okay? Best describe all the sample data. So this line is called our estimated regression equation, okay? All right, so this is when we do an estimated model. So for the estimated model, we still have two parts. The first part is the estimation of this deterministic line. And we know this part is stochastic, right? Stochastic. So deterministic line. So for this deterministic line, the estimated model is the corresponding estimation is called the estimated regression equation. Okay, regression equation. So you need to pay attention if the question in your exam is asking you what is the model or what is the estimated regression equation. Okay, so if you are asked the model, just write down the model. If you ask estimated regression equation, just write down the estimated regression equation, which is y hat. So we must put some hats on the estimated things, right? Y hat equal beta 0 hat plus beta 1 hat x1 plus beta 2 hat d2, for example, plus blah, 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 plus beta k hat xk. But never plus epsilon here, okay? Never plus the epsilon here because this is the estimated regression equation. It just stands for the straight line, okay? It stands for the straight line. Okay, so this straight line is actually y hat equal to blah blah blah. Okay, now beta hat times x something. So this is y hat. This means for any observed y, or for any given value of x, the value on the straight line is y hat. For example, if this is xi, the ith observation, then this value must be yi hat. However, there are still some difference between the actual value that we observe from the sample, which is yi, and our estimated value, right? So this difference, you can see, is actually pretty similar to the error term, right? It's pretty similar to the error term. So the first part, we call it estimated regression equation. Then the second part, we will call it residual, okay? We define residual as EI. And this residual is actually given by yi minus yi hat, okay? And we know that residual is actually what? Is actually some observation of the error term, right? So that's why when we are looking at assumptions of the error term, we'll be looking at residual, right? We will conduct a residual analysis in order to see if the error term meets the assumption, okay? So it took me years or 2 years, like ages, to understand the difference between the error term and a residual, okay? So now, finally, I understand. Error term is like a population error, right? We will never know exactly what the error is, right? However, if we take some sample and draw and calculate an estimated equation, then the difference between them can be regarded as a sample of the error term, which is the residual, okay? So the sample of the error term is called a residual. It's given by yi minus yi hat, okay? So if we combine them together, we know if it is an estimated model, it should include the estimated equation, which is y hat equal beta 0 plus beta 1 hat x1 blah, 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 plus beta k hat xk. And if you want to add anything like an error term, just plus a what? Plus a residual here, right? And then you will get y instead of y hat, okay? So this is estimated model, but I don't think you will be asked estimated model. Well, for example, if you're asked estimated equation or estimated model, just answer this part, okay? Answer this equation. It should be fine, all right? Okay. So let's do a quick recap of what we've done in step 2, because this is very important and very easy to make a mistake here, okay? So for model selection and estimation, model means a population thing, okay? It includes a deterministic part, which is the straight line, the estimated value of y, and also a stochastic part, which is the error term. And for this error term, we make assumption that it is normally distributed with the conditional mean of 0 and equal conditional variance, and each of the error terms should be independent to each other, which means no autocorrelation, okay? Beautiful. Now, for estimated model, it contains 2 parts. One is the estimated regression equation, and the other is the residual. So in your work, I mean in your major assignments, I saw a lot of students writing down the estimated regression equation is y the price hat equal some number plus some number x1 number x2 plus blah blah blah. Okay, all of those looks very beautiful. However, they plus an error term here. Oh my gosh. This shows that they don't really understand what's the difference between a model and an estimated model, okay? So when we make an estimated equation, it's just the straight line, okay, that we calculated from our sample. So why there are hats? Where there are hats? So if there are hats, we know they're probably random. Why are they random? Because every time you take a different sample, for example, now if I change to this red sample, probably the regression line should be calculated like this, right? So every time we take a sample, we will definitely get a different regression line. It's just like every time we want to estimate the population mean mu, we will get a different value of x bar. This is why x bar itself is a random variable, right? So here, for the population, we got beta 0, beta 1, beta 2, beta k, so many parameters. And if we take a sample and want to estimate all of those parameters, like beta 0 hat, beta 1 hat, beta 2 hat to beta k hat, they are never deterministic. They are random, because every time we take a different sample, the straight line will be different, namely all the parameters, like the intercept is different, the slope is different, so the intercept different, slope is different, okay? Have you got the idea? Good, very good. So that's all about step 2. You need to think about the model selection and estimation, okay? And another thing I want to mention here is, okay, I'll mention it later on, okay? Just forget it. Model selection and estimation, all right? Okay, so that's all about step 2. Now, step 3 is the easiest one. Oh, why am I using the red pen? Step 3. Step 3 is the easiest one. Step 3 is called prediction. Actually, the main purpose of performing a linear regression analysis is actually to predict the values. For example, if you create a linear regression model for like your final exam mark equal to beta 0 plus beta 1, your mid-semester mark. So you probably collect all the historical data from the old students, right? So for the previous students, and you know there are some relationships between final exam and mid-semester mark. And what's your purpose of having this equation? It's to make a prediction, right? Okay, so you want to make a prediction. So by plugging in your own mid-semester exam mark, what you can get? Your estimated final exam mark, right? Okay, the focus is probably, oh, hey? Okay, good. The focus has some issues. All right, so the questions are very easy here, okay? I don't want to talk too much. So they just give you the value of x1, x2, and dummy variable tell you is a male or female or which room type, and then you plug everything in your estimated equation and you can make a prediction. So very easy, right? Very, very easy, okay? So I don't want to spend too much time on this. But now let's come to step 4. In step 4, we are actually determining if the model is good or not, okay? It's goodness of the model. It can be the goodness of fit or the significance of the model or whatever, but we just want to see if the model works very well on the data, okay? So for the goodness of the model, one thing that we've learned is a group of R, okay? So the first block of knowledge that we learned is R's. So anything related to R's. So for R's, the first thing you need to know is the R square. The R square is calculated by SSR, which is the variation explained by the model divided by SST. Okay, so we basically prefer a higher R square, the better, which means sorry, what do I want to say? Okay, which means the model has explained the total variation in a large proportion. Okay, I feel sort of hungry. I forget to have my dinner, so that's okay. We'll finish very quickly. I think I can give you guys a question without giving you the answer. So by tomorrow night, I will hold another consultation and have that question together, because I got some very good questions for your practicing, but the problem is the printers in H70 is somehow not working, so I need to print it somewhere else. So I didn't print the question today. So do you agree that I give you the electrical copy or the soft copy of those questions, uploading them on somewhere, and I will create the link to this video, and you can get the questions. And after you try the questions, and you go back and we discuss those two questions together. Is that okay? Very good. That's a good benefit for everyone today. Okay. All right, now let's go back and see the R square. So all those questions will apply all the knowledge that we've covered today. So pay attention to the video today, and then you will be fine in those practice questions. Okay, it's a secret question. Okay, don't tell anybody. Okay, yeah. All right. Goodness of the model. So R square, and you should not only know what is SSR, SST, but you need to know it intuitively. For example, this is some samples, observations, and this is the regression line y hat equal to something, okay? So what do we mean by SSR, SSE, or SST? I'll do it quickly. For the least square estimated line, we know that 1 point must be on the regression line, which is x bar and y bar. X bar is just the mean of all observed x, and y bar is just the mean of all observed y's. So these two guys must be on the straight line. Now, for any of the observations, we can see for example, if we look at this xi and yi, okay, so if we look at xi and yi, so from this point we can see if x varies from x bar to xi, based on the straight line, where should the y be? It should be here, right? But I mean, based on the straight line, it should be here. So this part, or this variation, we can say that this part of variation is actually explained by this straight line, or by the linear regression model, right? However, there are still a part of variation that is unexplained by the model, which is this part, okay? And we know the total variation from the yi to y bar is this part. So we collect every single observation and try and calculate it, the variation explained by the model and variation not explained by the model and the total variation. Then we sum them and square them. We get a whole lot of SSR, SSE, and SST, okay? So firstly, what is SSR? I can tell you both of those sum of squares are just sum y minus sum y's. But now we need to know what y minus what y, okay? Let's look at it together. Let's see. The SSR is the part that is the sum of variation that is explained by this model, right? So it is this part. So this part is actually here is yi hat, right? And this part is y bar. Therefore, SSR is calculated by yi hat minus y bar. Square it, sum it, okay? And for SSE, it is the variation unexplained by the model. So we can see it is yi minus yi hat, right? Yi minus yi hat. Square it and sum it. So we can see yi minus yi hat is just what? Residual, right? So SSE is also called residual sum of square, okay? Residual sum of square. Because it's just the residual square, sum of square, right? Beautiful. Now, let's look at SST. SST is just the actual observed y minus the mean of y. So it's just yi minus y bar, square, sum. And we know, all of us will know, SSR plus SSE equal SST, right? So those are the things that you really need to understand in order to understand what is R squared, okay? So let's see. If we put all SST here, for example, this is SST, okay? We know it can be broken down into two parts. One is SSR, which is the sum of square that is explained by the model, and the other part is SSE, which is the sum of square that is unexplained by the model. So, if the model is good, do you think SSR should dominate all the variations or SSE? It should be SSR, right? If we want the model to be good, right? Okay, so this means if we take a proportion of SSR over SST, do we want it to be the larger the better or smaller the better? Larger the better, right? Okay, so from this picture, we can also see, have an intuitive understanding of R squared. So what is SSR over SST? I mean, the whole point, the whole thing is SST. It's actually the proportion of the total variation in Y that is explained by the model, right? Okay, so if you are asked to calculate the R squared, or it has another name, which is the coefficient of what? Of determination, coefficient of determination, and we know it's R squared, and we just find SSR and SST and calculate the results. And also, we will have what is next? Sorry, let me think about it. We will also have some explanation on the R squared. Sorry, I'm just too hungry, so I just my brain is just not functioning very well. Okay, so for R squared, how to interpret it? Just follow your lecture slides. It explained the percentage. For example, 7%. If we calculate R squared is 7%, then we know the 7% of the total variation in Y is explained by the model, right? So that's how we interpret the R squared. Okay. Now, R squared has a problem. What is the problem of R squared? So whenever we add a new independent variables, so if we add new independent variables, for example, we just increase the number of K, right? So what will happen to SST? It will remain unchanged, right? Because this one definitely not changed. Because Y is not changing, we just add one more X, right? So SST is not changing. Now, what about SSR and SSE? If we add a new independent variable. So if we add a new independent variable, the explanatory power or the explanatory value of the model must be increased, because even if it's not so relevant variable, it must explain some of the variations in Y, right? So what we can observe is that whenever we add a new independent variable, SSR will always increase and SSE will always decrease, right? So the result is that if we add 1 million independent variables, we can get R squared that is close to 1, right? However, that is ridiculous. So that's the problem of R squared. If we use R squared as a selection criteria for our multiple linear regression model, like which one of the variables should be included, which one should be excluded, then our conclusion will be we will include everything, right? Because R squared will be higher as long as we add new independent variables, okay? So, what should we do in order to modify this R squared and make it better? So what we're gonna do is actually to calculate what we call adjusted R squared, or adjusted coefficient of determination. And this adjusted R squared has sort of penalized on the number of independent variables. So it is calculated by 1 minus SSE over n minus k minus 1 divided by SST divided by n minus 1. So as we can see, this part is not changing, right? The only part that is changing is SSE and n minus k minus 1. So if we increase the number of independent variables, we can see a decrease in SSE. However, the degree of freedom here, n minus k minus 1, is also decreasing, right? So numerator decreasing, denominator decreasing. So what is the final result? Will it increase or decrease? It depends, right? So, namely, adjusted R squared can either increase or decrease based on whether SSE has reduced significantly and over the reduction on the K or on the degree of freedom, or SSE is not reduced that much and it not even exceeds the reduce in the degree of freedom. Okay, so this means if the variable we add is important, we can sort of expect adjusted R squared to be increased. Okay, and if not that important, we probably see adjusted R squared to be decreased. Okay, so that is what we have for the adjusted R squared and R squared. Okay, good, beautiful. All right, so new independent variable K. Okay, that's all about R and R squared. A subtle little thing that I want to mention here, probably you haven't learned it, but you saw it in your Excel output, which is the multiple R, right? Multiple R is nothing but the square root of R squared. So if you are asked to calculate multiple R, it's just the square root of R squared. And this one stands for the correlation between the y, the actual y, and your estimated y hat. So this is not a knowledge you learn from QBUS5002, but if you want to know it, and if you want to do the practice question, you probably need to know this knowledge. Otherwise, you'll be very, the confidence lights. Okay, what does this word mean? Not confident. Okay, you will not be confident. Okay, so that's all about step 4. Well, so far, let's stop here a little bit and quickly summarize what we learned for all steps in regression, okay? So for the regression, we started from understanding of data. We can use some charts or doing some critical thinking or business insight or the correlations and really understand the data and think about a draft of our model, right? So the second thing is our model selection and estimation. In this part, we need to know the difference between a model and an estimated model. So model has a deterministic part and stochastic part. So correspondingly, our estimation also have 2 parts. One is the estimated regression equation. So this equation is used for prediction, right? It's used for prediction. And for the residual, we know it's just a sample of the error term. So residual can be used to test on what? On the assumptions, okay, which is called residual analysis. So hopefully this will give you a whole picture or a big picture of the statistical model and estimated model, okay? All right. So we know the model is like a population and the estimated model is like a sample, okay? All right, that's all about step 1 and 2. And so step 3, which is very straightforward, just prediction. Just plug in all the numbers inside this equation and find your, estimated values. And for step 4, we want to know the goodness of the model. And the first thing we're going to learn is the R's. Sorry, the R's. The first block A. Block A is the R's. And now, followed. Now we're still in step 4, okay? We're still in step 4, but now we're gonna cover another aspect to see the goodness of the model. So basically, you probably need to consider everything in your major assignment in order to get full mark in your G question. Because some of you just use the significance t-test and forget to use some R squares or just the R square and see if the model has been improved or not. That's not a very convincing results or your convincing best model. Even though I know you did, nearly all of you deduct those 3 not important independent variables, but you know what I mean, right? Okay, so that's all about step 4. Now, step 5. Oh, no, not step 5. It's still on step 4, but B, overall significance. I can see a lot of problems in your major assignment. Everyone knows how to use overall significance and how to interpret it using your PowerPoint slides, lecture slides, and how to do the decisions, but your presentation shows not understanding at all of the overall significance test. So what is about this overall significance test? The null hypothesis of overall significance test is that we want to make a choice between if the model should be y equal to beta 0 plus beta 1 x1 plus beta 2 x2 blah 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 plus beta k xk plus epsilon, or it's simply a y equal beta 0 plus epsilon and everything here is 0, right? So for example, how that works. If you observe a sort of data like this, okay? So you can also work out a regression line. For example, some line like this, right? However, does this regression line really have any prediction power or predictive power? Actually, it's not really explaining the variation here, right? It's just like some random scatter, but you're forced to say they follow a straight line. So it's no better than saying all the y values is given by a constant value plus or minus the error term, something like this, right? It's just a constant value plus an error term. There's no strong linear relation here, right? So in this case, we will say the model is not significant because it's not really fit in the data. It's no better than constructing a model like a constant value plus a random number, right? Okay, so we just want to test if all those betas on the x variables are significant or not. Are 0 or not. So our test first, null hypothesis, is beta 1 equal beta 2 equal beta 3 equal beta k equal to 0. Okay, here is where the mistakes come from. So many of the students get beta 1 hat, beta 2 hat, beta 3 hat, and beta k hat equals 0. Oh my god. We are testing on the population parameters, right? What's the point of testing your sample statistics or your estimations? They are bullshit. It doesn't make sense, right? So keep in mind, your null hypothesis should always be beta 1 equal beta 2 equal beta 3 equal beta 2 equal. It's just like you need to put null hypothesis like mu equal to something instead of x bar equals something, right? No x bar equals something, it's mu equals something. Here are the same. It's beta 1 equal beta 2 beta k equals 0, not hat, okay? No hats. No hats, okay? So if you still put a hat in your final exam, and if I see it, I will put a green hat on your head, okay? I'll give you a green hat. Okay, sorry about that. All right. Alternative is at least one beta I is not equal 0. Someone would like to use K. It doesn't matter. I prefer I, okay? So the test statistic is now given by the MSR over MSE. And this one follows a F distribution with degree freedom 1 n minus K minus, sorry, no, it should be MSR. What is the degree freedom of MSR? It should be K, isn't it? And K n minus K minus 1. Okay, so this is test statistic and how the test statistic distributed. And for the decision rule is that either the observed value of F is greater than the critical value, which is F half an alpha K n minus K minus 1, you will be given the table if you are not given the output, okay? Or the p-value less than the significant level, which is alpha, okay? Because this is the one-tailed test, okay? So this is the one-tailed test. All right, one-tailed test. So that's all about overall significance. So if we reject, our decision rule is, okay, reject H0 if those two are meet, okay? So if we reject H0, this means at least one beta I not equal 0. This means this model is sort of valid, right? It's good. It's not that bad. But if we do not reject null hypothesis, this means all of those variables are just bullshit, has no relation to y. It's no better than a model like this, right? So what we're gonna do is just use this model. Just stop using the hypothesis testing. Stop using the linear regression analysis, okay? All right, however, overall significance can sometimes not cheat us, but yeah, I'll tell you later on about the multicollinearity problem. So that's all about overall significance. So far in step 4, goodness of the model, we first have a bunch of R's. One is R squared and updated versions, adjusted R squared, and some multiple R. In the second part, we know the overall significant test, which is the F test. And we want to make a choice between the linear regression model and the bullshit model, okay? And for the third block of knowledge, what we learn is individual test significance or individual independent variables, coefficient significance test. This is what we call the t-test, right? So for each if we reject the null hypothesis in overall significance, we know at least one beta I is not equal to 0, right? However, okay, Shuai Liu means at least one beta not equal is a one-tailed test. Yes, it is a one-tailed test. So why is it a one-tailed test? Because we want to compare MSR and MSE. So let's see what is MSR and MSE. So do you remember SSR and SSE, right? So if this is Y bar and this is X bar, okay? So this is XI, this is YI, this is YI hat, okay? So do you remember which part is SSR, which part is SSE, and which part is SST? Okay, good, beautiful. So the total part is SST, unexplained is SSE, explained part is SSR, right? So all the sum of squares are the sums. So if we want to look at individual observations, we generally want to take an average, right? It's just like when we calculate variance, we use the sum square of x minus x bar, right? Square. This is a sum square. But in order to measure the individual variation of each observation, we would like to take an average, like divided by n minus 1, which is the degree of freedom, right? Okay, so this is the same. So we have all the sum of squares here, but we want to know for the specific one individual observation, what is the average variation that explained by the model or not explained by the model. So we divide all of SSE and SSR by their degree freedom and create MSR and MSE. So MSR is SSR divided by K, and MSE is SSE divided by n minus K minus 1. So K and n minus K minus 1 is just the degree freedom of SSR and SSE. Okay, so then for each individual part, this one becomes MSE and this part becomes MSR, right? They are basically the same. Now, when do you think the model is significant? MSE larger or MSR larger? Definitely MSR larger, right? So if MSR is larger, this means the variation or the individual or average variation explained by the model is larger than MSE, right? Therefore, our overall significance test is simply want to test on whether MSR is larger than MSE, okay? Whether MSR is larger than MSE. That's why the decision rule is that observed value greater than the critical value, we reject null hypothesis, okay? So do we understand that? It is actually, oh, why okay, it's 10 o'clock, so I need to turn on the lights, okay? I'm still in ABS building. Okay, it's 10 p.m. So, that's why it's a one-tailed test. Can you see that? We're only interested in if MSR is significantly larger than MSE, okay? All right. So that's all about the overall significant test. Hopefully this one helps you. Okay, good, very good. Someone is asking, sorry to interrupt, but can we use financial calculator in our final exam? Thank you so much. Well, probably not. Just use a normal calculator, I guess. Actually, you can take both of them. And if no one like stop you using financial calculator, just use it. If someone stops you, you just take away your financial calculator and then use your normal one, right? Okay. Emma Cheng is asking if it is a one-tailed test, then the significance level of F statistics should not divide by 2. Oh, yeah. Sorry, I feel sorry. Here it should be alpha. Okay, here should be alpha. Sorry, I just used to half alpha, but forget alpha. Sorry about that. Yeah, here is alpha. Okay, alpha here. Thank you, Emma Cheng. Yeah, thank you, Emma Cheng. Okay, Jia Wei Yuan said we cannot use a financial calculator. All right, it depends, okay? If you want to use it, just use it. If not, just don't, okay? Well, just don't risk using that financial calculator. All right, let's move on to the individual coefficient significance test. For the individual coefficient significance test, we simply want to test on the significance of individual coefficient. So null hypothesis will be any of the beta I. Someone would like to use beta k, it doesn't matter. Beta I equals 0 or beta I not equals 0. Okay? So this is individual coefficient significance test. Now, the problem is what is the test statistic? It's still a t statistic. And as I mentioned before, it is given by beta I hat minus the hypothesized beta I, which is just 0. But we will have some question that is not 0 here, okay? Divided by the standard error of beta I hat. So the standard error can be found besides the coefficient column in your Excel output, okay? And this guy follows a normal, t distribution with a degree freedom n minus k minus 1. And the decision rule is that this is a two-tailed test. So if t observed greater than t critical, which is half an alpha n minus k minus 1, or the p-value less than significant level, we reject null hypothesis, okay? And this one is very, very easy, okay? Very easy. Good. All right. So that's all about individual coefficient significance test. So I also found a lot of problems in your major assignments, including some of them putting beta I hat here. Okay, same problem, right? Never put hat over here, okay? If I see you in your final exam, you put a hat here, I will definitely give you a green hat. One more, okay? All right. So, but sometimes you are asked to test, for example, H0, H1. We want to know if some coefficient is equal 0 or, equal to 1 or greater than 1, something like that, right? So in this case, you need to perform the test by yourself by calculating the test statistic, right? So T star test statistic is equal to beta I hat again minus beta I. So this hypothesis beta I just becomes this 1, right? And then divided by the standard error. This standard error can also be found beside the column of coefficients in the Excel output, okay? But in this way, you shouldn't rely on the p-value output in the Excel because you need to calculate it by hand. Because for the p-value in the in the Excel output is testing on if any of the individual coefficient is equal to 0 or not. But here, if you want to test it, if it is equal to 1 or 2 or 0.5 or whatever, then you need to, think about calculate this test by yourself, okay? So that's what I say about the final exam. Everyone knows individual coefficient significant test, but if I don't tell you, and there are possibility to test if it is equal 0, equal 1, or greater than 1, so this is a one-tail test, right? So in T observed greater than T critical, which is alpha n minus k minus 1, then we reject null hypothesis, right? Okay, so it's a one-tail test, so you need to, think carefully and read carefully of the question you are asked, okay? So it can be equal 0, not equal 0, but also can be equal anything. And then you need to plug in all the numbers here and then try and calculate the T observed value by yourselves, okay? All right, so that's all about the individual significance test. Last thing is the most problematic I've found in your major assignments, okay? Let's look at it together, D, which is the part D. Sometimes if we want to remove some of the model, some of the independent variables, and we want to see if our reduction of independent variable is valid or not, or restriction is valid or not, then we want to do a partial F test or a restricted F test. So the restricted F test is actually making a choice between the full model, which includes beta 0 plus beta 1 x1 plus beta k xk plus epsilon, and our restricted model. So the restricted model is y equal to beta 0 plus, for example, I just delete the last p independent variables here, okay? So here should be beta 1 x1 plus beta k minus p x k minus p plus epsilon. So, I removed a p independent variables, right? So what we're gonna be look at is actually, let's see. Let's go back and see our SST bar, okay? So this is our SST bar. It's very helpful in your understanding, okay? So for this SST bar, we know it has two parts. One part is SSR, and the other part is SSE. Now, let's see. If we remove P independent variables, what will happen to SSR and SSE? Exactly. So our SSE will sort of increase and SSR decrease. Is that right? Because we remove P independent variables. So the explanatory power of our model must be reduced, right? Okay, SSR reduce, SSE increase. So the only thing we want to see is that whether this part of change is significant to the changes here, to the original SSR or E. Oh, I can't remember. What's the formula? What's the formula of a restricted F-test? Do you remember? On the denominator, well, let's see. Firstly, let's write down the null hypothesis first. Null hypothesis is all the betas that you removed, like from beta p plus 1 equal beta k, all equal to 0. And your alternative is at least one of them is not 0, right? One of those beta i's is non-zero. Beautiful. So the test statistic F is actually given by, I think it should be the SSE, right? SSE. So let's see, how do we depict this difference, okay? So this difference should be, this is before we remove. This is after we remove. So this is the restricted model SSE. So this is SSE restricted, and the original SSE is the SSE unrestricted. So it should be SSE restricted minus the SSE unrestricted divided by the difference in the degree freedom, which is P. Is that okay? Beautiful. And divided by, okay, you tell me, divided by SSR or SSE of the unrestricted model? I can't remember. Can you tell me? Can anyone tell me what's the denominator of this restricted F-test? SSE unrestricted. Beautiful. So it should be SSE unrestricted divided by n minus k minus 1. Beautiful. Thank you very much. So we just want to see if the deduction in the SSE, the increase in the SSE after we remove all the p's is significant to the original unrestricted SSE. Okay, so we want to see if this part compared to this part is large or not. Okay, so this guy follows the F distribution with degree with freedom of P as well as degree of freedom n minus k minus 1. Okay, so for the decision rule, we know again the observed value greater than critical, which is F alpha. Again, it's a one-tailed test. P n minus k minus 1, we reject null hypothesis, or if the p-value is less than alpha, we reject null hypothesis. Okay, so when we reject null hypothesis, we know that this part is significantly large compared to SSEU. Is that right? So then we reject null hypothesis. We cannot see any of them. We cannot say all of them are not significant. So at least one of the beta I is non-zero, so the restriction is invalid. Okay? All right, so that's all about the restricted F-test. So someone is saying okay. Oh, someone retracted the message. Okay. Oh, what is that? Will we be provided SSE for both restricted and unrestricted model? Probably yes. If not, you'll probably be given SST and SSR, and then you calculate SSE by yourself. Okay, so don't worry, you will be given, I guess. Later on, I will upload a question for all the audiences today. and we will discuss that question tomorrow night. Is that okay? Good. And in that question, you'll be calculate those F tests manually, and you will find how it can be asked. Okay, beautiful. All right, that's all about step 4. It's a lot of things, right? Goodness of the model, right? One is the R. We have R squared, adjusted R squared, and multiple R. Overall significance, which is F test. We need to pay attention on the null hypothesis and alternative hypothesis. Shouldn't be any heads. And for the interval, for the individual coefficient significance test, yeah, okay. I was distracted by someone's message. Okay, I'll discuss that later on. Okay, for part C, individual coefficient significance test, make sure never put a hat on the beta. Okay, for the null hypothesis and alternative, and this is test statistic and decision rule. And lastly, restricted F test. So all those 4 tests are for the goodness of the model. Okay, so that's all about step 4. All right, all about step 4. Now, let's look at the last step of today, and then I can have my dinner. Sorry, it's not finishing, okay? We still have step 5. Step 5. Step 5 is easy. It's your last question in your major assignment, which is the assumptions. Okay, let's list all the assumptions for the multiple linear regression model. Can we? Let's have a try. What are the assumptions? So, as I mentioned, there are some assumptions about the error term, which involves some residual analysis, right? Okay, so first of all, the first assumption is that the error term must follow a normal distribution, isn't it? Okay, so normal distribution, error term. Secondly, the error term should have no correlation with x, which means the expected value, the expected mean, a conditional mean of error term should always be 0. Okay. Thirdly, constant variance. The variance of the sigma epsilon hat given any x should also be 0. And fourthly, the correlation between any of the 2 error terms should also be 0, which is sort of autocorrelation stuff, right? And fifthly, no multicollinearity, which means the correlation between any independent variable x should also be 0. And sixthly, oh my gosh, it's unique for QBUS5002. All like values or samples are observed without error, right? So this one we don't need to test on this one, right? Observe without error. This is the basic requirement of everything, right? We cannot observe errored or biased observations. Okay. So for each assumptions, let's see how can we test it. First one, normal. We use what? Histogram. Beautiful. If we look at the histogram and it looks like a bell-shaped, then it should be normal. Okay. So there probably be some problem in your final exam, like discuss on the validity of the assumptions of the linear regression model and give you a lot of charts, a lot of plots, and you need to determine if any of the assumptions is violated or not. Okay, so first one, histogram. The second one, conditional mean. And let's combine 2 and 3 together because we can simply judge it based on residual plot. What I want to mention here is it is residual plot, okay? Residual plot. It's not standard residual plot. Many of you put standard residual plot in your assignments. I can't say it's wrong, but it's not that precise, because when we standardize a residual, we are not dividing it by the same number, okay? So it's not a complete equivalent to the residual plot, okay? So it's residual plot, not standardized residual plot. But luckily, I didn't deduct any mark if you put standardized residual plot, okay? It's just me, perfectism, okay? All right, residual plot. So how can we see if the conditional mean is 0? So conditional mean is for any given x or any y hat against any y hat or whatever. If you observe something like this, what do you think? So for smaller x or smaller y hats, we can have a mean of negative, right? A negative mean. And for the values of y hat here, we sort of have a positive mean. And here is 0, but here again negative, here again positive. So do you think the conditional mean is always 0? Not really. Sometimes 0, but sometimes negative, sometimes positive. So this assumption is violated from the residual plot. Now, what about the third one? The third one has another fancy name, which is called homoscedasticity. So if this homoscedasticity means same variance, right? So if this one is violated, it's called heteroscedasticity, okay? It's called heteroscedasticity. All right, so we generally observe heteroscedasticity when the conditional variance is not equal given any y hat or any x, okay? So we can see, all right, for small value of y hat or x, the variance is small. But for the larger the y hat or the larger the x, the variance becomes larger. The variance becomes larger, right? Okay, so we can identify the existence of those two independent variables using a residual plot. The fourth one is basically about the time series data, because only in time series data we will have a problem of autocorrelation, right? So for testing of autocorrelation, you just look at the residual, sort the residual by date, okay, and see if you can find any patterns in the residuals. For example, in the cyclical effect or seasonal effect or whatever, right? So you just see if there exists any autocorrelation here. In 5001, actually, we learned what we call Dubin-Watson test to test on the autocorrelation, but you are not required in this unit study. Okay, so for time series data. So if it is not time series data, for example, it is sectional data, then it has nothing to do with time series, with autocorrelation, okay? Fifth one, multicollinearity. So for multicollinearity, we just look at the correlation matrix as what we did in the first step, right? Look at the multicollinearity and see if there are multicollinearities between independent variables, okay? You must remember it's between independent variables. Never look at the relation between y and x because they are supposed to be very high, okay? Only look at the correlations between x's, okay? All right, so that's all about the multicollinearity. And in QBUS5001, or in some of your major assignments, you also consider VIF as a measure of, as a test on the multicollinearity. They're also good, but not in our unit of study, okay? All right, so far, that's all about the 5 assumptions of multiple linear regression model. Come on, wow. We know we use histogram to see if it is, histogram of the residual, okay? Oh, I sort of forget because, you know, whenever we are talking about error term, we know it's a population stuff. So we can only have some observations of residuals to be a sample of the error term. So everything deal with the assumption of error term, we will do it by the residual, the observation of residual, okay? Look, time series is also plot the residual over time or over date, okay, and see if there is any patterns. All right, so that's all about the assumptions. Oh, so far it seems like we finished all the knowledge of today. And for time series, ratio, and what? And financial mathematics, if you got problem, just leave it in the chat log, okay? I think we still need one more consultation tomorrow. Do you think so? So later on, I will upload the questions I mentioned today, and the link will be directly underneath the description of the video. I mean, after this live streaming, there will be a video recording on this video on the same channel, okay? So just subscribe the PLG channel, and then you will find the link in the description. So try the practice question by yourselves, and tomorrow I will check the answers with everyone, okay? Beautiful. So let's do a quick recap of what we've covered today. So firstly, we started from the understanding of central limit theorem. Most of the students are encountering issues in the central limit theorem in their mid-semester exam, I can tell. So central limit theorem gave us sampling distribution of sample mean and sample proportion. So by knowing there's sampling distribution, we can construct confidence intervals or do hypothesis testings. So we have a general form of confidence interval, which is given by point estimator plus or minus critical value times the standard error of the point estimator. And for hypothesis testing, we also have a general form of the test statistic, which is given by the standardized version of the test statistic of the point estimator, right? So by standardization, we minus the mean divided by standard error, we got a standardized test statistic, okay? And the decision rules are all determined by like based on one tail, two tail. I think it's easy for all of you. And then we come to the regression, and we know regression has a lot of things to consider, but when we put a whole picture and break them down into 5 separate steps, then we found that, oh, everything we've learned has been included in a logical way, right? So that's pretty awesome. Step 1, we need to understand the data. So this is what you initially do in your major assignment, right? And step 2 is to choose the best model, or not best model, but create the model. Oh, it's not selection, it's creation, right? Creation and estimation. Because for selection, we need to do it after step 4, right? Repeatedly. Okay, in this part, we need to know the difference between model and estimated model, okay? So we also need to know the difference between the deterministic line and the estimated equation line. Estimated equation. We need to know the difference between the error term and the residual. And we know that since error term is the population concept, so whenever we want to test on the assumptions on the error term, we need to think about the residual as their observations, okay? And step 3. Step 3 is just prediction. I don't want to talk much. Prediction. Plug in the number and get everything done. Step 4 is a bit more to be included. We got a bunch of R's. What are R squared, adjusted R squared, multiple R, and what is the overall significant test, whether it is a one-tail test or two-tail test, right? I've explained the rationale behind it. And C, individual coefficient significance test. So you should not only consider the 0 scenario, but also all other scenarios, right? Lastly, restricted F test, and then followed by step 5, assumptions. Now, let's look at the questions from the students. First of all, Olivia Lee is asking, we cannot use the calculated number for beta coefficient when writing the model, can we? No, we can. Yes, you are right. Because if we are asked what is the linear regression model, then you must put the betas over there, okay? Because all your observations or all your calculations of betas are the beta hats, right? They are estimations. But if it is model, oh, where is my page? I can't find it. Oh, it's here. Whenever you ask the model, you need to write down this stuff with the error term. But it's estimated equation, you write down y hat with the numbers here, number here, number here from the Excel output. Okay? So does this answer your question, Olivia Lee? Any question else? So the calculations will only be used in the interpretation. Yes, it will be used in the interpretation, but also it will be used in the estimated regression equation. So if it is asked, yeah, you are right. Yes, beautiful. Okay, any other questions? I can see there are still 20 of you watching, and we still have 1 minute left. Any last minute questions? Oh, they are really last minute questions, right? Any last minute questions, guys? Last minute. I'm waiting for your questions. If you don't, I will upload the practice question immediately after we finish the live streaming. So everyone will download the question and have a try. So Ripu Zhengra is asking tomorrow night, can we discuss about stratified sample mean and variance of stratified sample, please? Oh my God. All right. I hate that topic, but all right, sure. Okay. Super Yan is asking, when will the next live be held? What about tomorrow night, the same time? Is that okay? Super Yan, is that okay? So Jia Wei Yuan is asking how many weights you have. What do you mean by weights? Do you mean body weight? I've got roughly 74K. Yeah, 74K. Any other questions? Any other questions? If not, we will call it a day, okay? That's all for today's live streaming tutorial or live streaming consultation. Thanks for watching. So if you like it, just click on the like button, and if you dislike it, don't click on the dislike button. And if you want more video from us, just smash the subscribe button. Thank you very much. Enjoy your Monday night, and good luck to your bus like 50-80 exam tomorrow. Good luck, okay? All right. I will upload it right now, okay? See you guys. Bye-bye.